Okay, decided to do something different this morning with John Denver, Country Roads, and just sort of a nice, lighthearted music from the past. Questions on radicals. I'm nearly afraid to ask this morning, given that these have the potential for being distracting. But are there questions you'd like to ask in 9-2? Jennifer, was that a hand up? I couldn't tell. Okay, which one?
I had trouble with the ones with variables, but number 53.
5-3. So this is a specific case of the more general problem. Is that what I'm understanding? Okay, so 53. I'm still trying to get... Okay, let's try that, Debbie. My comfort level with what I'm getting out of there isn't always that good. It's the square root of what? 400x to the 6th? Is that correct? So let me just leave that there. And then the question of what we're going to try to get, 400x to the 6th. So the key, if you were looking at square roots, is to understand there's what? An index of 2 understood. That's like a half power for an exponent. So I'm going to look for perfect squares. Now, a lot of ways you can see this problem. One is just write the answer directly. But if that's not something you see, then the question is, what else can you do? You certainly can do this. And to that extent, the square root of 400 is 20. Perfect square. So you can pull out the 20. And now we're back to that problem yesterday a little bit where I had the cube root of z to the 9th, which was z to the 3rd. Well, the square root of z to the, or x to the 6th is x to the 3rd. Now, if you can see that immediately, you're there. You could have seen it where? Right out of here. Going from here to here possibly. But if not, maybe here. Now, if this still isn't hitting you, then what could you do? Maybe see this as x to the 6th to the what? 1/2 power, because the square root means the exponent is 1/2. So 1/2 times 6 is 3, therefore x cubed. Jennifer, does that help? And again, each problem is going to look somewhat different in terms of the variables that are included. If I just did a slight tweaking of this and said, for example, that I had the square root of 800 x to the 7th, okay, then what you would want to see is breaking that up as 2 times 400 times x to the 6th times x to the 1st. And so what you're trying to do is factor it into perfect squares. Now that's a much more difficult problem than the one we had. Okay. And the question, of course, if you look at that, you might instead see 4 times 200 instead of 2 times 400. The key is you've got to see perfect squares in your head to know how you're going to break it up. Now, if I can take out the 400 as a square root and say that's 20, I can take out the square root of x to the 6th and say x cubed, and I would still have inside 2x. And that would be considered simplifying the radical, which involves an earlier problem you've done, and this is considered simplified. So it's not always possible to pull this out directly, like we pulled out x cubed from x to the 6th. Here you would have to see that as x to the 1st times x to the 6th, then pull out the square root of x to the 6th as x cubed. Do you have another one you want to look at in that same way, or does that answer? Okay, anybody else with a question on this? Okay, Jeff, I was noticing in one of the problems I went through in the homework where just a comment coming back because we're doing a lot of these with the square root of a sum of two squares, where we had things like, just a minute, it was a 64 and a 225, so I think it was 64 and 225. So we had an 8 and a 15.
I know where I screwed up on that.
Okay, and it looked like you were taking out parts instead of adding first, and then, so just a comment, you have to go ahead and add first before you get the square root, and so just be cautious how you break these up, and what may seem intuitive that it should work, you want to check to make sure the numbers are working. This comes out, of course, 17, and this is an 8, 15, 17 Pythagorean triple. Okay, which is, again, a little different one for what we've been doing. Any other comments or questions? Okay, I'll go with that then. Let's pass that set in. I'm very pleased that you aren't getting frustrated at the level I thought might be possible. Okay. Oh, why not? I mean, I was just told I can't therefore frustrate you today because that would break the frustration barrier or something like that. Okay, I want to talk about adding and subtracting radicals. Now, again, this gets into watch your intuition. Be careful. We have said, just a reminder, that if I have the square root of x times the square root of y, I can do what? What's the right side of this? The square root of xy inside, right? We argued that, and I can take the nth root, nth root, nth root, so it doesn't just have to be square roots, cube roots, fourth roots, fifth roots, etc. Now adding them instead of multiplying them. Now I have to pick a number here in my head. Square root of 8 plus the square root of 18. Now, there is nothing short of putting decimals for those that you can do at the moment. However, we are going to look at this as our objective, to simplify that expression into a nicer expression if you didn't have a calculator handy. Okay? Now, I've rigged this problem. The answer is not to add 8 and 18. Multiplication works, the addition doesn't work that way. Can you do something to simplify the square root of 8 for me? Okay, 2 times 4. So you could argue that that's the square root of 4 times the square root of 2. And that's nice because what can be done with the square root of 4? 2, and then you'd have the square root of 2. So I have 2 to the square root of 2. Any light bulbs go on yet? Okay. Yes. Okay, what about square root of 18? What are you going to see? Aha! Square root of 9. Square root of 2. And the square root of 9? 3. And I have 3 to the square root of 2. Now, if this was 2x plus 3x, you would say 5x. So I'd like immediately to be able to go and say 5 the square root of 2. However, maybe you would prefer to see the square root of 2 taken outside as a distributive property of factoring. This is for Jennifer. This is Jennifer's factoring. And then 2 and 3 is 5, so you have the square root of 2 times 5. But what's bad about that? We mentioned that yesterday. Because you don't know if I mean 2 or 25 inside. So to avoid that confusion, I do what? 5 in the front and the square root of 2, so that it's clear that that radical ended at the 2 and not the 25. Now, I was very careful in what I did. Let's say I instead had given you this problem. By the way, would you make a suggestion for an index that would have made this a piece of cake? 3, yes. If I had the cube root of 8 is?
2.
Cube root of 27 is? 2 and 3 is 5, and you'd be done. But I didn't. I gave you square roots. So go on. This is the square root of 4 times the square root of 2, correct? Same as before. And this is what? The square root of 9 times the square root of 3. Breaking it into perfect squares and something else. So now what do I get? 2 the square root of 2 plus 3 the square root of 3. You're done. Nothing can be done to this answer. But when I had 2 the square root of 2 plus 3 the square root of 2, I could go the extra step. You can't factor out a common factor from here. Where I was able to do that is we just tweak a little bit right there where I factored out the square root of 2. I could do that there. I can't do it here. Do you see the difference between those two? There are times, no matter how badly you want to do something, you can't do it. That old thing by Kenny Rogers. You have to know when to hold and when to fold. Okay, this is when you fold, you say you're done, stop, go on to the next problem. Don't wishful think your way into this and say, I got 5 somethings. Doesn't work. Okay. The problem set starts, and I'm going to ask Debbie to go back to the document cam for a moment, because, and I'll have to level the book a little bit, but that first problem was what I was just talking about, where you take out the square root of 2, and you're ending up with the 11 the square root of 2. But the number 3, go ahead, still on there, number 3 can't be factored, because you had 1 the square root of 2 plus 2 the square root of 3. You can't simplify it any further. Then number 4, look at that one. The square root of 3 versus the cube root of 3. Just because you have the same thing inside the radical sign, what must be still the same? The index has to be the same. So we talk about visual cues. You see a radical, the first thing that will pop into your head typically is square root. That's a visual cue. If you see a radical with the 3 as an index, you've got to focus on the index, not just the radical. So what is being said here, you have to develop a level of sensitivity that goes beyond seeing the square root symbol. You're so ingrained, as we come back to the board for a moment, what is being, as an example here, where I have the square root of 2 added to the cube root of 2, nothing can be done there because the index as a square root versus a cube root makes them different. The fact that you have a 2 inside each and you see a radical inside each, you can't ignore the index. And of course, we don't usually write the 2 because it's understood as what? As a square root. If in doubt, sometimes it helps to go this route. 2 to the 1/2 plus 2 to the 1/3. Different exponents. Can't do anything about it. It's like x to the 3rd plus x to the 2nd. You can't do anything to that to simplify. Now, you might be able, to say 2 to the 3/6 plus 2 to the 2/6. Now I'm talking about what? The 6th roots. So that's the 6th root of 8 plus the 6th root of 4, and I can rewrite it, but it doesn't do me any good. I still can't combine them. But at least the roots are the same now. So you can sometimes modify the radicals so they are the same if that helps you. That pushed you a little bbit maybe too far. But working with fractional exponents, this was originally 2 to the 1/2. And then I had 2 to the 1/3. And all I did was find a common denominator for the exponents. Hence, 3 over 6, 2 over 6. So that means I had the 6th root of a 2 cubed, and 2 cubed was 8. The 6th root of 2 squared, which was 4. And there's nothing I can do with that. Well,
Would it be 4 to the 5?
yeah, well, But what we could do, you're close, you're very close, because I could say that's the 6th root of 4 times the 6th root of 2 plus the 6th root of 4. Oh yes, this is good. Because that's the 6th root of 4 times the 6th root of 2 plus 1. So you can play and have fun. That's sort of a Math 90 level, to have fun that way. Okay? I'll just leave that there for a moment. Okay, let's go back to sanity. I'm on page 539 in a moment, if I can get the problem I want in clear relief. There we go, Debbie. 16. What can we do with 16 to make that work? Okay, we have minus 4 to the square root of 75 plus 3 to the square root of 24. What could you do with that? Okay, you see the 75 is what? 3 times 25. Okay, the square root of 24. 4 is a perfect square. That's about the best you're going to get. Is that right? So we're supposed to subtract or add whenever possible. I'll try to slide that just a little bit more. Now the thing here, understand not all the problems are written with the idea that you're going to be able to bring closure the way you want. So this is going to be a little more frustrating. So not too much, Michelle, just a little bit. We have minus 4 to the square root of 75. And then I'm going to have what? 3, the square root of 24. And what I have to now see is factorings with perfect squares. So I want you to see the square root of 25, the square root of 3, and here what? The square root of 4, the square root of 6. But all that's going to give me is minus 20, the square root of 3, plus 6, the square root of 6. Do you see anything else I could do?
2 times 3 on the square root of 6.
Okay, 6 is 2 times 3. So I don't know if this is expected, but let's see what we can do. You see that last step? But now it's Jennifer time. Square root of 3s and everything, right? Jennifer, right? Okay. So I have the square root of 3 times minus 20 plus 6, the square root of 2. Did that gain me anything? No. In fact, it looks worse than what I started with. But that would have been a step I could have done. I think the intent was right here where I'm putting the check marks, that was the intent for your answer. So there wasn't anything that could be done there particularly. Debbie, let's go back to that set and see if there's something better that we could do in number 13. Let's see if 13's any kinder to us. So I have what? 5 the square root of 72, and I have minus 3 the square root of 50. Okay? Now, we're going to approach this the same way. Your approach is to hunt for what? Perfect squares as the factoring. So when you see 72, what should you see? Well, 9 and 8 would work, but 9 is not the biggest square. Go for a bigger. 36 and 2. Very good. Now, could you have done it if you had seen 9 and 8? Yes, because what might you have then seen? If you got the 9 and 8, then you might say, wait a minute, yes, I have the square root of 4, the square root of 2, and you're still going to get there. Because anyway you cut it, this is going to be 3, this is going to be 2, so you have a 6, which is what you're getting out of here. So your 5 times 6 is going to give you 30, and you're going to get 30 to the square root of 2 any way you do it. So even if you didn't see the 36 and you saw the 9, you get the 8, and you think of the 8 being broken up into 4 and 2. So it's not like you have to see the largest or you can't do it. Okay, next step. What about the 50? 25 and 2, that's probably an easier one to see as opposed to the 72. By the way, 5 and 10 is getting you nowhere, because 5 and 10, neither one are a perfect square. So the 5 and the 3, negative 15, the square root of 2. So down here I'm going to have negative 15, the square root of 2. Now at this point, are you comfortable in just saying 15, the square root of 2? If you're not, what can you do? Factor out the square root of 2 and have left the 30 minus 15, and you still get what? 15, the square root of 2, because what's my argument? I don't want the 15 after the 2, I want the 15 in front of the radical. That is the preferred form. Let's go back to the document camp for a moment, Debbie. Can you just off the top of your head see the answer to number 7 without even working at it? As you look at the screen? Yeah, the square root of 17 plus 4, the square root of 17. What do you get? Now be careful. What's in front of the first square root of 17? Understood. A 1. So it's 5, the square root of 17. And so it's that 1 that didn't get written as a coefficient, but it's understood. And that's the trap. You're going to be inclined to say, I got 4 the square root of 17. No, because you factored out the square root of 17 and had a 1 plus 4 left. So you have to be cautious. Well, one would suspect things are going to get more interesting. Sort of like potato chips, well seasoned. 540. Okay, last things with 3 terms in them. 22. Okay, what are we going to do with 22? Has a nice poetic ring to it. 22. I have 6, the square root of 18. And I have plus 2, the square root of 48. And I have 6, the square root of 28. Somebody got hung up on the 8s. Okay, what can we do with this? Well, 18 you see is what? 9 and 2. So, it might be nice as an intermediate step, maybe to do that. But while I'm at it, what am I going to do with the 48? What do you see? Is 12, okay, 12 and 4, that's good because 4 is a perfect square, but 12 has a perfect square in it. It would have been 4 and 3. So what could you do instead? 16 and 3? I would have preferred, I think, the 16 and 3. What about the 28? The 4 and 7, I heard. Yes. Now, could I have done this with a 4 and a 12? Yes, because I've had the square root of 4, and then the square root of 12, but the square root of 12 is the square root of 4, the square root of 3, so it would have worked. Okay, are we ready to simplify now? The 3 out of here, so 18, the square root of 2, then what? 8 the square root of 3, 12 the square root of 7, and fold. Yeah, there's no common factor. You have the square root of 2, you have the square root of 3, you have a square root of 7, but none of those are common in each of the terms. Now, you might ask, is that any better than what I had up here? Not particularly, except if I had a limited number of square roots, the square roots between 2 and, say, 10, then I could do this without a calculator. Up here, I'm going to work a little bit harder. That would be the only argument at the moment. Okay, back to our page, and so we did that. Looking at those, at 18, do you see something nice there as you just look at 18? Because the 44 can be done as what? Square root of 4, square root of 11, that's nice. And then that 99 is the square root of 9, the square root of 11, and suddenly there's a square root of 11 and everything, and you're in business. So if you can see 18 and say, that would be nice, and you look at 22 and go, oh, that's sort of bittersweet. I did all that work and nothing good happened. You're getting the feel of it, even if you don't want to. But it gets better. How about number 30? We have the square root of 4a minus the square root of 16a plus the square root of 100a. What do you see that's good? The a and everything, right?
And all square roots, actually.
And you have a square root of a in all of them, and are you going to get a square root of 4a in all of them? That's what you'd like. So let me write the problem. We have the square root of 4a minus the square root of 16a plus the square root of 100a. What do you see in the second radical? A 4, unfortunately. Okay, let's see. We can take out the square root of 4 and get 2. So the first one is 2 the square root of a. Then this one is 4 the square root of a. Oh, that's good. And 10. The fact that we have perfect squares and everything was what made this one nice. Okay, when I first saw it, I saw the 4a and I saw a 4a here and a 4a here, and I could have done that. In fact, I got the square root of 4a times 1 minus 2 plus 5. However, let's just do it here. What do I get now? The square root of a, if you prefer. Now you could do this part in your head. But 2 minus 4 plus 10, which is 8, agreed? So where am I going to put the 8? In the front. 8 the square root of a. Now, is that the only way you could have done that? No. I could have looked at this and said I have the square root of 4a, and then I can take a 4 out of there, which is the square root of 4, which is 2 in the square root of 4a. And then I had 25 times 4, so 25 is 5. So 5 the square root of 4a. So that would have been the square root of 4a times 1 minus 2 plus 5, which is there are times when the mind just stops, right? Says, no, I'm not going to do that. 5 and 1 is 6, minus 2 is 4. Okay, so we have 4 the square root of 4a. But what do you suddenly wake up and realize? The square root of 4 is 2, so that's really 4 times 2, which is 8 the square root of a. Same answer, approaching it in a different way. Which is the better? The first one, the more direct route. One of the nice things in these is no matter how you tend to see it, it eventually does go where it should. Now the downside, the more steps you have in these processes, the more likely what's going to happen. the production process is going to at some point glitch on you, and it doesn't take much to mess it up. Okay, let's go back to the book. We need to get something even more challenging than that at this point. What do we got up there that we can see? How about a fourth root? That is intriguing. I'm going to slide down a little bit. There we go. Get it in the middle of the page. Maybe if I drop that down just a little bit. There we go. 44. Oh, that looks interesting. 44. Now, what can we do there? 44. I have 5 the fourth root of m to the 5th. Now, we have to change our thinking here a little bit. 3 the fourth root of 81 m to the 5th. Now, the difficulty here, you have to think fourth powers, not squares or cubes. What do you see when you see 81? Typically, if I just gave you an 81 and I asked you to factor it, would you see 9 times 9? Typically. But 9 is 3 squared. So if you have 9 times 9, you have 3 squared times 3 squared, which is 3 to the 4th. So the fourth root of 81 is 3. Okay, this goes back to Jennifer's question today. M to the 5th. What do you have to see in the m to the 5th? We talked about this earlier. Because I have a fourth root, I'd like to see this as something to the 4th. So what I would like to see is 5, the fourth root of m to the 4th. I didn't write that 4, so you can see it as an exponent as clearly as I'd like. So we have the fourth root of m to the 4th times the fourth root of m, technically to the 1st. Then I have plus 3, the fourth root of 81, the fourth root of m to the 4th, the fourth root of m. Now I'm trying to go back to that early question. What do I have to see when I have the letters in here? If I'm at the fourth root, I want fourth powers. That's the key. So what is the fourth root of m to the 4th? M. So I really have 5m, the fourth root of m. And I'm not making that 4, so it reads well enough that I think somebody looking on the monitor is going to feel good. That better? Yes. Now, what about this next mess? Okay, the fourth root of 81 is 3. So I have 3 times 3, which is 9. And then the fourth root of m to the 4th is m. And then I have a fourth root of m. You aren't done. Because now I got common stuff. I don't know if you want to do this as factoring. You probably, I hope you're comfortable in saying m, the fourth root of m, times 5 plus 9. Do you see that? Or you could just say, these aren't variable factors in the same way. But whatever is multiplied by the 5 is the same thing that's multiplied by the 9. So I have 5 of the same thing that I have 9 of. So I should have 14 of whatever it was. Well, that's a vague expression. But 14m, the fourth root of m. You're done. Thank you. 14m, the fourth root of m. Now that would be considered simplified. Your life isn't, but the problem is. Back to the book. Okay, 42, looking at that, what do you see in 42? And now I just want to look at it from the standpoint, what are you going to look for? You're in cube roots, good. So what do you feel good about as you eyeball the problem? Has it been rigged for you? That's my question. Has the problem been rigged? What's your argument? Anybody?
Yes. They're always rigged.
I'm going to comment they're always rigged. We've seen a couple that weren't rigged. So what makes this rigged? What do you see about 54 that's good?
Once you take out the cube, you're going to have
Take out the cube. What are you looking for? Go ahead.
you're going to have a single k on each radical, I believe.
Okay, but I want the numbers. Let's look at the numbers for a moment. What's good about 54 if you have a cube root? And it hasn't anything to do with the 9. Okay, let's come off there for a moment. Cubes. Think cubes for me. 1 cubed is 1. 2 cubed is 8. 3 cubed is 27. Back to the document, Cam. Do you see 2 times 27 on the 54?
Now that you mention it.
Okay, so the question, because what's obvious when somebody shows it to you is not obvious necessarily when you're doing it. Let's look at the cube root of 54. What can be done just with that number that may work? Let's come back to a 9-6 that somebody saw. I'm going to put a dot for multiplication. Could you build on that if that's what you saw? Somebody give me an argument.
No, because I'm not seeing anything cute.
Okay.
You can pull a 3 out of there. couldn't you?
Yes. But what I want you to see is the 9 is 3 times 3, and the 6 is 3 times 2. Now, if you keep pulling it apart, what can you eventually see? That you have 3 to the 3rd, and you have the cube root of 3 to the 3rd, which is 3. Now, I just about made the classic blunder. I left the 3 out here. And I think you're going to find yourself doing that. You write the 3 here, you write a new radical, and because you're so comfortable writing a square root symbol, you'll forget to put the 3 in, and then I'll have to do something.
Radical.
Oh, do something radical, I take a point off, right? But do you see how I can get the 3, 3, 3, even though I didn't see the 27? So what are we back to? Prime factoring as a possibility. Okay, let's go back to the document, Cam. Okay, we had a 16. Now, your problem when you see 16, you're still thinking squares, and that's 4 squared. Okay, that's good, but what should you see? A 2, 2, 2, which is an 8. So 16 is 2 times 8. So the cube root of the 8 is a 2, so you're going to have 2 to the square root of 2, where in the first part we had 3 to the square root of 2. So the point is, how do you break things up? And the answer, if nothing else, with primes, right? Okay. Now the question, as I look at the other problems there, because there are not enough of them that lend themselves to what I want, but I think in 43 I can contrast something, because we just looked 16 and said think cubes. Now here in number 43 in the screen, what is my second radical? A 4th root, correct? I'm on number 43, and I have the 4th root, because the index that you're seeing on the second radical, and I'll try to point that out, right there. That 4 means the 4th root. So how do you have to see 16? Not as a perfect square, but as a what? 4th power. Okay, so coming off there, we've got to create a new table. 1 to the 4th is 1. 2 to the 4th is 16. 3 to the 4th, we just saw, 81. 4 to the 4th, 256. 5 to the 4th, 25 squared, which is 625. They get harder, right? So instead of thinking that way, what might be better? 16 could be factored into 4 times 4, which is then 2 times 2 times 2 times 2. You have 4 2's multiplied together. So the 4th root of 2 to the 4th is 2. Factoring works better than memorizing perfect 4th powers. Get the idea? As you look at those, is there anything that appeals more or less to you? Yes?
My question might be simple, but I don't know. Like in 43, it says 5 times m to the 3rd.
Okay, be careful. And he said 5 times m to the 3rd. It is 5 times the 4th root of m to the 3rd.
So we can't pull that m to the 3rd out. We have to just leave it inside, right?
Precisely.
We can't do anything else with it.
Exactly. So you have a 4th root of m to the 3rd. The only way you're simplifying that is the second radical you can write as 16 now, the 4th root of m cubed. Since you have 16 of them, 5 of them, you're at 21 of them. Good point. What is the key there? The exponent on the variable has to be more than the index. So if you had m to the 5th and you were taking the 4th root, you could do something. M to the 6th and a 4th root, you can do something. But an m to the 3rd with a 4th root, nothing can be done. Good point. Any other questions as you're looking at these? Because I can't get a sense of what you may be struggling on unless you share it. Because what I may clarify for you in an example I do up here, when you suddenly are given the right key, you say, oh yeah, I see that. But doing it at home alone, I've never thought. Home Alone 1, Home Alone 2, Home Alone in Algebra? Okay. Yeah, oops. Giving you just the wrong kind of goosebumps, right? Shivers up and down the spine. Home Alone. Okay, going on. Are there any questions here that you would like to look at in specific? You look at it and say, I don't see how I would approach it. Let's see if we can help. We should be playing Simon and Garfunkel, The Sounds of Silence. Any question at all? You're looking at those and you're comfortable. Feels good.
There's always those fractions up there, like in 23.
Yeah, I looked at the fractions earlier. What Pam is looking at is, she said 23 and I heard 24.
Yeah, looking at either or.
Just because I'll probably do the odds, and I've done a couple odds that I shouldn't probably have given away. Okay, Debbie, let's try that. Now, because there's a fraction, there's just a tendency to do what? Automatically skip it. Go on to something that doesn't have a fraction. But what should you be focused on instead? The radical signs. They are both what? Square roots. That 2/3 you see isn't an index. So it's the square root of 27 and the square root of 48, and you should feel really good about a 27 and a 48. Why?
3.
The 27 is 9 times 3. Now what would you want ideally? A 3 in the next one. So that may be a hint. 3 times 16. Okay, let me put that one on the board. And I'm starting to run out of board, so I don't know what I'm going to do very soon here.
Would it be wise to like factor out the...
Pardon?
Would it be wise to get rid of the fractions right off the bat?
Okay, good question. Let me write the problem. And we're asking the question, can I do something to get rid of the fractions so they don't cause me anxiety? Okay, here's my problem. Would there be something I could do with those fractions it isn't an equation, so I can't multiply both sides by an LCD and say, goodbye denominator. Wouldn't work, because no equation. And the only thing that you might consider is replacing them with decimals. But then I have 2/3 as an infinite decimal, a 0.6 forever. That isn't going to help. Instead, what you're going to see is the 27 can be written as the square root of 9, the square root of 3. And of course, the fact that the square root of 9 is 3 means the 3 and the square root of 9 will cancel, so it might be worthwhile to put 1s under that. So I'm going to be down to what? 2 the square root of 3. So to that extent, I did get rid of the denominator. Okay, the next one. 3 over 4. What are you going to see in the 48? Well, we said because there was a 3 that came out of here, just like in factoring before, you might find a hint. Maybe a 3 is a factor there, and indeed it is. And you should suddenly have an appreciation for what the author has done for you and how considerate and kind and benevolent. Because the square root of 16 is 4. The 4's are going to cancel, and I have 3 the square root of 3. So yes, I did get rid of my denominators. Now at this point, you may be feeling so good, you say done. Because the denominators are gone. But you've got a square root of 3 in both of these. So I can do a factoring and take that out and have what? A 5 in front and now. And isn't that nice? That mess came down to this. You would have never thought that that collapses to 5 the square root of 3. They don't always work this way. Sometimes you go through this much and you're done. Otherwise, if this had been instead of 27 and 18, I would have had 2 the square root of 2 and 3 the square root of 3, and that's it, and I'd be done and nothing else. You can't force on a problem a solution that's not there, and there's going to be that inclination. Going back to the document chem, indeed, that was a good problem with fractions, and I think Michelle's question is an excellent one, because there's a way that we have been able to avoid denominators. When we had a complex fraction, we multiplied the numerator and the denominator by the LCD. When I had an equation with fractions, we said multiply left and right side by the LCD. Goodbye denominators. I don't have a complex fraction in this one. I don't have an equation in this one. So I'm stuck with the denominator unless I can cancel. And it worked out nicely that I could cancel. But I think that's a good question, a very good one. Other problems in this set that you look at and you say, potential trouble. Bless you, half. That was a half sneeze, so a half bless you. And that's like a square root of a bless you, because that's a bless you to the 1/2 power. Page 541. This is sort of forcing the issue. You've got a rectangle with 7 the square root of 2 and 4 the square root of 2, and you're supposed to find the perimeter of the rectangle. So the perimeter is 2 times the length plus 2 times the width. So you have 2 times 7 the square root of 2 plus 2 times 4 the square root of 2, and you're supposed to simplify. Sort of neat. Okay, as we come off there, just a comment, if you've ever written books or manuals and try to get examples, doing them is not easy. Writing the words is the easy part. Coming up with good problem sets is really tough. And like we talked about, let's come back, Debbie, for a moment with camera 2, to the 24th, the very last problem. What would you be doing at night that you would think of that problem? Give thought to it. I mean, you're writing problems for a book. And you want to come up with something that works nicely. So you sit there and you've got a glass of wine, a warm fire going, and you're trying to think of neat problems that are going to work. Now, I admire that one. That one is so neat because it all just works so well. Now, this one, again in the document, Cam, getting a rectangle like this and saying, hey, we have a 4 to the square root of 2 and a 7 to the square root of 2, I think he had one too many. Yeah, we're at the bottom of the bottle and the precipitate is getting there. And it's, how many times are you going to see a rectangle with a 7 to the square root of 2 and 4 to the square root? It just doesn't lend itself to me in the same way. There is one more set of problems at the very end, and this, I realized as I graded last night's work, one of the things that I didn't do as we look at this problem now, I didn't do much with the finding the distance between 2 points, and I felt very badly after I'd finished that if we look at this problem, or two of them, 51 and 53, you understand that these would be coming out of the distance formula, where you're subtracting y2 minus y1, x2 minus x1, you square the difference, you add them together, and you take the square root. Now, the only reason I bring that up, you again have radicals involved there. Now, this is a calculator problem where you're supposed to understand order of operations. And I think it belabors the issue a little bit. Again, why are we going through all this work with radicals? Because they occur naturally when you find the distance between 2 points. And we talked about that formula that we're going to use to solve a quadratic equation in one variable. And we get square roots when we do that, and you're expected to simplify them in a way that gives you elegant looking answers. Now again, let's come back to 24 one more time. I'm really enamored with that answer. 5 to the square root of 3, that's elegant. It's so much more elegant than 2/3 the square root of 27 plus 3/4 the square root of 48, which is a mess. And you can simplify that down to 5 the square root of 3. That should just make you feel warm. You got a nice looking answer. Okay, what about the homework problems? I can't sell much today, it seems like. I think you're going to find, if you are able to key in what we've talked about today, this might be an easier set than last night's. Maybe. We'll start with number 5, and we'll go up to number 44. So actually 5 to 43 odds. So number 5 to 43, the odd numbered problems. The green stuff's after, isn't it? So the green stuff's after 43, so we don't have to worry about that. The green stuff, is that like spinach and broccoli? And okay, the green stuff. Now, I just want to let you know where we're headed, because I did this problem already, and I just want you to realize what's up next. The next section, on 542, we've been there. Rationalizing a denominator so that we're dividing by something that isn't a decimal that goes on forever without repeating. What was my example? Something like 1 over the square root of 5. Instead, remember that? We have 1 over the square root of 5, just to remind you there. I'm going to, let's see if I can find the statement. Yeah, I don't even find a nice statement that allows me to focus on what I want. Not good. Here's the example given. I'll just put that on the document, Cam. The square root of 3 over the square root of 2. The argument is, if we look at that one, it's not quite as maybe neat as just saying I have 1 over the square root of 5 or 1 over the square root of 2. If I look at that, let's zoom in a little bit tighter because I'm not going to need much space there. I don't want to divide by this decimal because it goes forever. So if instead I multiplied the numerator and the denominator by the same thing, so I'm multiplying by 1, I'm replacing this denominator with a what? A 5 now. So I have the square root of 5 over 5. Now, if I want to do this longhand, and I know what the square root of 5 is, dividing by 5 is a pretty easy operation. But if I want to divide by the square root of 5, and I carry it out 4 digits and say, no, I want it more accurate, then I have to completely do a new division problem. Here, if I want more accuracy, I just carry out more digits and continue my division. This is considered preferred. This is considered rationalizing the denominator. So back to the document cam, what would you do in that one? You want to get the square root of 2, so it's just a 2. So I'd multiply top and bottom by the square root of 2. So I would have, when I get done, the square root of 6 over 2 that you can see in the step right below. And I've shaded that enough, I think it comes up. That's called rationalizing the denominator, and that's what we're going to do. We just have to get clever at times. We'll talk about that tomorrow. So you know the homework assignment. And Debbie, we opened with John Denver. What are we closing with?
John Denver, and I chose rhymes and reasons.
Rhymes and reasons. That's radical. That's good. Have a great day.